I'm standing. Let's say, sure, 600 feet from a launch pad. And a rocket, a toy rocket, blasts off at, sure, let's say 40 feet per second. It's traveling at 40 feet per second. How fast is the distance from myself to the rocket changing when, or yeah, it's changing 20 seconds after takeoff, blasting off. All right. So clearly we draw a picture. See, I'm standing 600 feet from the launch pad. So here's me. Here's the launch pad. And then there's a rocket blasting off, going this way, up. So here's the rocket. Excellent picture. It looks so rockety. And we're asking how the distance from me to the rocket is changing. Okay. So as we usually do with related rates, we're going to label the things that are changing. So this distance, which I'm partial to calling h, but you can also call anything you want. I'm going to call it h. That distance is changing. And this distance is changing. I'm going to call this, I usually call it s, because that's what someone taught me to do once upon a time. So those are the things that are changing. This distance is not. That distance is staying the same at 600 feet. So now, I usually write this down, right? I start off by saying, okay, what's changing? S is changing. In fact, that's what we want to know, right? We're curious about what ds dt is equal to. And then we also know that the height is changing. And we know that dh dt is the rate of change of the height, or the change in position with respect to time, or the velocity of the thing, or the speed, if you like. That's going to be 40 feet per second. Right, the height is changing at a rate of 40 feet every second. The rocket is going up 40 feet every second. We're pretending that there's no, we're not worrying about gravity. We're pretending that the rocket is perfectly powered, that it exactly goes 40 feet per second for as long as we care about. At least 20 seconds. Okay. So then we need an equation relating the things that are changing. Often, especially in the 21 series, this is going to be some geometric equation. In fact, we'll finish this problem, and then I'm going to take a minute to talk about geometric formulas you should know, because you do need to know them for these related rates problems. You're also going to need to know them when it comes to optimization problems, which is coming up after the graphing stuff. So I'm going to take a minute to talk about those just so you guys have seen them, and then we'll move on. We'll finish this problem first, because we should. All right. So what have we got here? We have got this picture. Here's H, here's S, here's 600, here's me. Ooh, me. And we're going to write an equation relating the things. In this case, it's going to be the Pythagorean theorem. So you get 600 squared plus h squared equals s squared. And while you could try doing some solving, you usually just want to differentiate right after that. So second step, write the equation. Third step, differentiate. The derivative of 600 squared is 0, right? 600 squared is just 360,000. And the derivative of 360,000 is 0. The derivative of h squared is 2h times dh dt. The derivative of s squared is 2s times ds dt. And then we're going to plug in what we know and solve for what we don't. But where am I going to plug in that time is equal to 20 seconds? Well, I'm not. I'm going to use the fact that dh dt is equal to 40 feet per second to say that, oh, well, if the rocket's going 40 feet per second and it's 20 seconds after blast off, the rocket's going to have gone 40 feet per second times 20 seconds. The seconds cancel and you get 40 times 20, which is 800 feet. So at the moment of interest, the height is 800. So I'm going to get, I can also cancel the 2's, right? Let's just cancel the 2's. So I get 800 times dh dt, which is 40 feet per second. I don't really want to write the units until the end. Equal to s, which I also don't know. And I can either use the Pythagorean theorem, or I could guess that it's probably going to be one of those nice ones, and it is. Right? This is just a 3, 4, 5 triangle where all the sides are multiplied by 200. 3 times 200 is 600. 4 times 200 is 800. 5 times 200 is 1,000. A lot of the times when you're dealing with triangles and you're using the Pythagorean theorem, people have come up with triangles that are going to be nice multiples of a Pythagorean triple. Like 50, 120, 130 would also be another one, right? Because the 5, 12, 13 right triangle all multiplied by 10. Or you can use the Pythagorean theorem to find the third side is 1,000. S is 1,000. And we're looking for ds dt. So 800 times 40 is 32,000. And then divided by 1,000. That's going to end up being 32 feet per second equals ds dt. And it does make sense that it's less than 40, right? If you're going up at 40 feet per second, this length can't be increasing any faster than that, right? Because you're not, like, for the length to be increasing at its fastest, you have to be kind of traveling directly away from someone. But we're not traveling directly away from you, right? We're going up and I'm standing over there. So it does make sense that it's less. I should also go ahead and say something that people often ask in conjunction with this question is the follow-up question. How fast is the angle of elevation to the rocket changing at the same moment? So the question people often ask is, what is d theta dt? And I guess, I can erase this. So bonus question, lucky us, bonus. How is the angle of elevation changing? 20 seconds after blast off. Okay, so just like before, we need to find an equation relating the thing that we want to know is changing and the thing we know is changing. Now, I will mention here, you could have an equation that involved s, but I'd rather not. Yes, we know how s is changing at this one moment. At this moment of interest, we do know that ds dt is 32 feet per second. But I would really like to be able to answer the question about theta without having to have done this work, right? So we're going to ask the question about theta, pretending like we haven't done the first part of this. So I want to know what d theta dt is. And I do know, once again, that dh dt is 40 feet per second. So the thing here, to get an equation relating theta and h, well, typically the way you relate an angle to one of the sides of the triangle is through a trig function. So there's two good answers to this question. What trig function can I use so that I have h in my equation, but I don't have s? I really want a trig function that for theta that has h and not s. So what's one option? Tangent, definitely an option. Is there another option? Anyone else want to tell me the less favored stepbrother of tangent? Yeah, exactly. Stepbrother might not be the co-function of tangent. Yeah, you can also use cotangent. Now, I will point out, in this case, I would use tangent because tangent of theta is equal to h over 600, or as I'm going to write, 1 over 600 times h. But if for some reason I was talking about this angle instead, I would actually use cotangent, because cotangent of this angle is h over 600, and I'd rather use the trig function that makes it so my variable is in the numerator, right? Because if my variable is in the denominator, I have to use like the quotient rule. I'd rather not, and I don't have to. In fact, I'd rather even make my life slightly easier here and say, that's debatable. No, I guess I wouldn't. I thought I wanted to. I don't really want to. So let's take the derivative of both sides. What's the root of tangent? Secant squared of theta times d theta dt. And the derivative of 1 over 600 times h is 1 over 600 times the derivative of h, which is dh dt. All right. I feel like I should talk a little bit about units here. Well, we'll see. So secant squared of theta. So secant, I never remember secant. I probably remember it. I know that cosine of theta is adjacent over hypotenuse. And at the moment of interest, that's 600 over 1,000, which is 3/5. So that means that secant of theta at the moment of interest, 20 seconds after blast off, is 5/3, and secant squared is going to be 25/9. So looking at this here, plugging in what I want to plug in, I get 25/9 times d theta dt equals 1 over 600 times 40. Now, I really should talk about the units for a second. Tangent of theta here is h feet over 600 feet, which means there aren't any units, right? When you take tangent of an angle, you get a ratio, right? Tangent of this is that over that, some number of feet over some number of feet. So tangent of theta is just like no units. It's a dimensionless thing. So when you're asking about how theta is changing, you're getting like something per some unit of time. So what we're getting here is, well, first of all, let's do the multiplication. We're getting d theta dt. Let's simplify this a little bit to, I guess, 1 over 15, right? 40 over 60 is 1 over 15. Times the reciprocal of this, which is 9 over 25. Cancel a 3 there and a 3 there. You get 3 over 125. Somethings per second. If we're talking about angles, it's got to be not degrees. Degrees are a unit. Radians don't have a dimension. This is radians per second. And the way you might justify that to yourself, if you're not sure, is that when we say something is, pi radians, what you're actually talking about is you're saying, oh, it's pi radians because you're talking about the length of the arc length, which is some length divided by the radius, right? Or I know it's been a while, maybe a long time, but the way you calculate the angle in radians is the angle is the arc length in maybe feet divided by the radius in also feet. And the feet cancel, and radians are a dimensionless unit. Okay, enough about that. But so generally what you do is you just be like, okay, I get some number, it's always radians per whatever unit of time, unless someone asks you for degrees, which is crazy. So this angle is increasing at 3 over 125 radians per second. Okay. So that said, before we go to the problem I said I was going to do, if you don't remember what it was, some linearization problem. I did say I would briefly talk about. So it is important to know how to find the various geometric formulas for things. Meaning, so for 2D shapes, and this is important for both related rates problems and optimization. I mean, there are other things as well, but that's where this is coming from. So two-dimensional shapes, we got circles, the radius of r. We know the area is pi r squared. We know the circumference is 2 pi r. We know that the diameter is 2 times r. You know, the circumference is, I mean, I'm kind of going extra here. Really, you probably just need like these. But you should also know the diameter twice the radius. You should also know the circumference is pi times the diameter. And I guess while we're at it, since I just was saying it, if you take an angle of theta and you call this arc length S, S is equal to R times theta. In my opinion, this equation is pretty much the same as this equation, right? The circumference, the arc length all the way around is 2 pi times the radius, or the angle all the way around times the radius. Just like any arc length is the associated angle times the radius. Kind of neat. Okay, so circles. What else we got in 2 dimensions? We've got squares. I know I'm doing the easy ones, but still, right? So, right, area is x squared, perimeter is 4x. That's all I can think of when it comes to squares. We got rectangles. Rectangles with a length and a width, or x and y, whatever you want to, right? Area is length times width. Perimeter is 2 length plus 2 width. Other 2D shapes. I feel like sometimes you run into trapezoids. Or no. And I should mention, right, when I say trapezoid, you probably think of this particular looking shape or something like it. But a trapezoid is really any shape where you have 2 parallel sides and 2 non-parallel sides. So it can be this. It can be something more like this. It can even be something wonky like those are all trapezoids. I mean, obviously, where we're pretending like these lines are parallel. In any event, for each of these trapezoids, if you call this the height, then the area is given by the height times what I like to think of as the average of the bases. Right, where you're calling this B1 and this B2. Oh, I guess I missed triangles. How did I miss triangles? Good job. Yeah. Triangles. They don't have to be equilateral. They can be kind of anything. Area is 1/2 base times height. Perimeter is just you add this. So there's no like nice formula for perimeter. You just add the sides together. There are some wacky triangle formulas, but that's the one that you should know. And then, of course, for a right triangle, we have the Pythagorean Theorem. So sorry if this is boring, but I do think it's important. So I'm trying to get through it kind of quick. So I suppose 2 other triangle things you should know are, sorry, it's like a weird shot. I'm sorry. Okay. So 2 other triangle things you should know is for right triangle, you should know the Pythagorean Theorem. And then for similar triangles, it's also important to know some stuff. So the thing about similar triangles is really people are just talking about trig functions. So if I call like this x and this y and this a and this b, there's so many things you can write down. You can say x is to a as x plus y is to b. Basically, base is to height as base is to height. Or you could say x is to x plus y as a is to b. Small base to big base is small height to big height. Or you can write like all sorts of different ratios. Or really, you could write like 6 different ratios because there's 6 different trig functions. But the last one I would probably notice here is, I guess you could flip either one of them. But really, what I'm really looking at here is if I look at this angle for a second, what I'm really just doing when I write x over a, I guess I'm writing cotangent. Cotangent theta is this side over this side if that's a right angle, or this side over this side if that's a right angle. Yeah. Or for x over x plus y, I guess that one isn't the trig function. So those are all the two-dimensional things off the top of my head that I can think of that you probably need to know. There are also some three-dimensional things. Which might be a little more interesting. So let's go from easy to hard. Let's talk about a cube. Looks like this. Has an edge length of x. The things I would want to know is the volume is x cubed. Why we call the third power the cube power. And the surface area is just the sum of the areas of the sides. Each side has an area of x squared. There are 6 of them like a die. Okay. Rectangular, oh gosh, there's a rectangular prism. Or more fancily called a parallelepiped. Something looking like this. Right. My picture is not the best. If we call this x, this y, and this z, the volume is x, y, z. And the surface area is kind of annoying. It's this rectangular area. It's all the rectangular areas added together. So it's xy twice. It's, it's xz twice. And it's zy twice. Okay. I think 2 more shapes. Maybe 3. Yeah. Sorry, I'm running out of room. Too many shapes. Okay, we have a sphere. With a radius of r. The volume is 4/3 pi r cubed. And interestingly, and I think I've probably said this before, for a cube, the surface area is just the derivative of the volume. The derivative of the volume is 4/3 pi times 3r squared. 3's cancel. You get 4 pi r squared. To me, this is one of the interesting things that is true about circles and spheres, is that the derivative of their larger dimension thing is equal to their next smaller dimension. Okay, so the derivative of volume is surface area, and in the circle, the derivative of area is circumference. I know you all are very impressed by that interesting fact. It is interesting. It's not true for other things, right? For a cube, the volume is x cubed, and the surface area is not 3x squared, it's 6x squared. So don't confuse this piece of information for anything other than what it is. Last 2 shapes. Cylinder. With a height of h and a radius of r, has a volume that is pi r squared h, And a surface area that is maybe a little bit of work, and this actually is important when you take 21B because you talk about finding volumes of things using cylindrical shells. The surface area, the volume is, yeah, but the surface area is also kind of important. The surface area, if you've got the top and the bottom and the sides, well, the top's a circle, the bottom's also a circle, so we've got two circles. And then the side, the around part, I like to imagine a roll of paper towels, where I took off one paper towel that went exactly all the way around, and I unrolled it. And when I unrolled it, I got what kind of shape did I get?
Rectangle.
Yeah, a rectangle. Sometimes people say a square because specifically paper towels are more kind of squarish, but you're right. More generally, it is a rectangle. And the rectangle has a height of h and a length of the circumference. So the area here is 2 pi rh. And so that gets added onto the surface area. This is, of all the formulas that we talk about, this is probably the one that people have the hardest time remembering. Is that the surface area of a cylinder with the top and bottom is 2 pi r squared plus 2 pi rh. Sometimes people will talk about like a cylinder without the top, because they're talking about like something shaped like a cup. And then it's just 1 pi r squared plus 2 pi rh. So, and then lastly, this one's easy if you know the cylinder is a cone. With again a height of h and a radius of r. So for a cone, the volume is the same as the volume of a cylinder with the same radius and height, except it's 1/3 of it. So 1/3 pi r squared h. I definitely remember, like in high school, which I know was many years ago, there was, I think it was actually in my chemistry class, my chemistry teacher had like a plastic cone and a plastic cylinder with the same radius and height, and you could take the cone and fill it with water and then pour it into the cylinder, and provided you didn't spill too much, you could do it exactly 3 times, and the volume of the cone 3 times it was exactly the volume of the cylinder. So it was kind of a neat visual or physical thing to actually like, oh yeah, this cone really is 1/3 the volume of a cylinder with the same radius and height. And the surface area, no one in their right mind should ever ask you about the surface area. It's kind of a wonky formula. I know I saw it just recently, but don't worry about the surface area of a cone. If anybody ever wants you to do something with it, they will tell it to you because no one expects you to know the surface area of a cone formula. All right. So typically, your math teachers going forward will expect you to either know these or know how to find these very quickly, because they're going to ask you questions or they might ask you optimization questions like, you've got a cone inscribed in a sphere of radius 6. What's the biggest cone by volume that you can have? And you're going to need to know the volume equation of this and some equations about that. So just be aware, these shapes are assumed to be known in all their kind of splendor. All right, hopefully that wasn't too not interesting. Let's get back to the interesting things. All right, let's look at, let's look at this question. So somebody said they want to estimate, and this is why I talked about this other stuff first. They want to estimate the volume of material in a cylindrical shell. I'm going to change the numbers to protect the innocent here. It says length, I'm going to say height. Of height, 50 inches. A radius of 8 inches. And a thickness of 0.25 inches. So So let me draw what we're looking at. And so we don't want to actually calculate this, we want to estimate it. We could actually calculate it, I'll talk about how. But here's how we're gonna, well, here's the picture we're looking at. So we've got a cylindrical shell, meaning I don't have, or a better word for this would be like a pipe. Right? A pipe that maybe waters, I mean, a fairly, not, I guess, right? Yeah, right. So it's better, so it's like a 16-inch wide pipe. That seems good. Maybe like that, yeah, like that. 50 inches long, because we're only looking at like a cross section of it for some reason. And water's like going through it, right? So there, it's a pipe. Yeah, that's a good physical interpretation. So I want to know how much material is actually used in making the section of pipe. Well, I want to approximate it because I don't want to do that much math. So the way you could actually calculate it, oh, and I guess I should say, so I'm making the assumption that the inner radius is 8 inches. It doesn't matter actually if we're just estimating whether it's the inner or the outer radius, but I'm going to write that the inner radius is 8 inches, which means that the outer radius, right, is 8.25 inches. So if you actually wanted to find the actual amount of volume there was, so the actual amount of material would be the volume of the large cylinder minus the volume of the small cylinder. So it would be pi times the big radius. Wow, that's not how you write 8.25. Minus the volume of the smaller radius, of the smaller cylinder, or the inner cylinder that isn't there. So this is how you could actually calculate it. Now, I will say, this seems like a lot of, this would definitely require calculus. So this is the big cylinder, right? That's the outer cylinder. And then we're subtracting off all the volume that would be in the inner part. But again, I don't really want to calculate 8.25 squared times pi, right? It's not impossible. It's just what we want to do. So here's what we actually want to do. We want to approximate the change in volume using a differential. So the change in volume, which I'm going to call delta V, can be approximated by the differential, which is dV. I'm going to find dV is I'm going to use the derivative. So I've got all these nice pictures here. Sure. So I know that the volume of my cylinder in general is pi r squared times 50, right? I would say h, but my height here isn't changing. Let's just say it's 50 pi r squared. Let's find the derivative of this, and let's talk about what that means. So the derivative here with respect to the radius, so when I say the derivative with respect to the radius, I'm really saying, we're saying that the volume changes so much as the radius changes, or how the volume is changing as the radius is changing. So dV dr, if I take the derivative of this, I just get 50 times pi times 2r, which is 100 pi. I know it's tempting, sorry, 100 pi r. I know it's tempting to want to write like a dr dt or something because you're thinking kind of like related rates. There's no, remember, nothing about how things are changing with respect to time. We're talking about how volume is changing as radius is changing. So here's what I really want to say. What this means is that if the radius were to change by like 1 inch, the volume would change by 100 pi times 1 inches. Another way to see this is this dV/dr is the slope of the tangent line of the function for volume. So this tells me that if the independent variable changes by so much, the dependent variable changes by 100 pi times that. I didn't quite say that right. I said that kind of wrong, and now I feel terrible about it. Because really, yeah, sorry, I kind of boned that one. Let's try it. Let's back it up just a little bit. This r here is not how the radius is changing. This dr is how the radius is changing. I apologize. So what I should really have been saying is that dv is equal to 100 pi r times dr. Because it matters, and I was missing this before, so really like back up, it matters how big the radius is, right? If I take a pipe that's, say, 4 inches in diameter and increase it by 1/4 of an inch, that's going to be a different amount of volume than if I take a pipe that's 8 inches in diameter and increase it by 1/4 inch, right? That 1/4 inch gets you more material if your radius is bigger. So what I really should be saying is this. The approximate change in volume is equal to 100 pi times the radius times the approximate change in radius. My radius was 8 inches. This is going to be 800 pi times dr. So 800 pi times dr, the dr here is the change in the radius, which is 0.25 inches. So that's going to be equal to 800 pi times 0.25, which is 1/4 of 800 pi, which is 200 pi. So the amount of material that's used to make this pipe with a cylindrical shell is approximately 200 pi cubic inches. But again, what I really want to say, right, is that we know that the volume depends on the radius. And we know that as the radius increases by so much, the volume increases by 100 pi times the radius times whatever that increase is. We can also calculate this just to kind of compare. So just to let you guys know, if we calculate this, I can factor out the 50 pi, and I'm really just looking at 8.25 squared minus 8 squared. If we look at 8.25 squared, which is 68.065, minus 8 squared, I get 4.0625. And 4 times the 50 pi would give you 200 pi. So 4.0625 times the 50 pi is about 638, whereas 200 pi is how useful? 200 pi. Sometimes this calculator kills me. It's about 628. So our estimate of 200 pi, which is about 628, is a slight underestimate of how much material is required. It's actually 638. But what I really want to point out is that you can estimate a change in volume. And I'm really viewing this as a change of volume. I'm thinking it's the change of volume when the radius goes from being 8 inches to 8.25 inches. You can estimate a change in volume by the differential, where again, the differential is just the top part of the derivative. So you're really, I know it's not a fraction, but we treat it like a fraction. We're really just multiplying the dr over and saying, oh yeah, dv, the approximate change in volume, is 100 pi r times dr, where 100 pi r is how the volume changes as r changes, and then we're multiplying by how r is changing. Okay. Or if you prefer, right? Slope of the tangent line, or rate of change, times how much the input has changed, gives you how much the output has changed. All right, I think I've said enough about this. But if there are questions, now is the time you should ask them. Okay. So I should mention, there was one mean value theorem type of question I didn't really talk about last week. And it was the following type of question. So most of the mean value theorem type of questions are find the values of C guaranteed by the mean value theorem. And that just involves taking the derivative of your function, setting it equal to, so again, right, this is a reminder of the mean value theorem. Mean value theorem essentially says, I'm not going to write all the stuff. It says if your function meets the things, right? It's continuous, it's differentiable. Then there is a number C between A and B such that f prime of C is equal to f of B minus f of A over B minus A. Or, in other words, in other words, the instantaneous rate of change is equal to the average rate of change, somewhere between the endpoints. And again, the function has to be continuous and differentiable. So there is another type of question we can ask, and it's a little bit more complex. Someone sent me a good one, which I think we will look at. So here's the type of question. Show that, really the type of question is show that blank equation has one solution, meaning exactly one. Not two, not three, not zero, one and only one solution. So, and here's the question, here's the function in question. Show that the equation x plus sine squared of x over 3 minus 8 equals 0 has one solution, or 1, 0. Either way. 0, root, solution, they all kind of mean the same thing. Okay, so this is actually a really good example. So if any of you ever think about being a math major, well, one, my friend would say, don't do it. But I personally like, I was a math major, I think it's great. But the thing you're about to see is an example of what's called an existence and uniqueness proof. And it's definitely, even if you're not a math major, it's something you'll probably see when you take 22A or maybe 22B, but definitely 22A. So this is an existence and uniqueness proof, where to show there's exactly one of something, you first show that there is at least one, right? We show there is a solution, and then show that there can't be two or more. So first, the existence part. So really, also, I was writing this question, I would have phrased it as show that this equation has exactly 1, 0. That's a little bit more precise way of asking this question. So first we show it, and I probably spelled existence wrong. I feel like this would be an E, not an A. Doesn't matter. Nobody cares about your spelling. In math, anyway. Most of the time. Unless it's spelling a different word that actually is something different. Then people care. Okay, fine. So how do we show an equation like this has a solution? The good old intermediate value theorem. So first, let me ask everybody, is this function continuous? Yeah, it's continuous. X is a continuous function. Sine is continuous, so sine squared is also continuous, and of x over 3 also continuous. Minus 8 for sure. So this is definitely a continuous function. So I'm going to try and find two values where one makes it positive, one makes it negative. But I'm going to use 0 because 0 is easy. So let's plug in x equals, so first and foremost, let's call this f of x. F of x equal to x plus sine squared of x over 3 minus 8 is continuous. Personally, I don't think you need to verify this. I think you just need to say it. You need to see it with your eyes and be like, cool, it's continuous. I should tell everyone else I know it's continuous. Done. Second, more important part, we have to find a place where it's positive and a place where it's negative. I am always going to pick 0 if I can to plug in. So let's try f of 0. F of 0 is 0 plus sine of 0 is also 0. Minus 8. Great, that's going to be super easy. Negative 8, that's definitely negative. Here's another key piece of advice. I know sine, whatever sine is, always has output values between -1 and 1. So at most, this is going to be 1. This is going to be 1 minus 7, which is -7. So for this to overcome the negative part of -7, I need this to be probably bigger than 7. Probably bigger than 8. In fact, why did I just pick 8? I mean, 8 seems kind of dumb, but okay. If I picked 8, I know that sine squared is always non-negative. So 8 plus a number that's bigger than 0, well, actually, bigger than or equal to 0. Maybe I shouldn't pick 8. Minus 8 will be negative. So maybe what's a number that's easy to take sine of that is for sure bigger than 8? I have one in mind. Let me ask you even more easy. It's a multiple of pi. What multiple of pi is bigger than 8 for sure? Someone's like 100. You could say 100. Nobody said 100. You could pick 100 pi, right? You could say 100 pi plus sine squared of 100 pi over 3. I don't even care what that is. Minus 8. That's definitely bigger than 0. But yeah, thank you, Ryan. 3 pi is actually what I was alluding to. Right? If I pick 3 pi, I get 3 pi, which is bigger than 9, plus sine squared of 3 pi over 3 is pi. Sine of pi is 0. Minus 8. So 3 pi minus 8 is 3 pi minus 8. And although I don't know what number that is, I'm definitely sure. Well, actually, I do know what number it is. It's 3 pi minus 8. I do know that it's approximately 1.4 or something. I definitely know it's bigger than 0. So check, check. And then we can say by the intermediate value theorem, there has to be a solution. So by the IVT, there is a number C between 0 and 3 pi such that f of C is equal to 0. So great, we've shown that there is a solution, but we're not done. We want to show that there is only one solution. Like Highlander, there can be only one. Okay. Okay. So part 2. So now the uniqueness part. So typically in mathematics, to show something is unique, meaning it's the only one, you assume it isn't. You say, well, I'm going to pretend like there's 2, or maybe even more. Usually 2, though. And then I'm going to, through some series of logical arguments, reach some impossible conclusion. In this example, the conclusion we're going to reach is that we're going to violate the mean value theorem, or specifically actually Rolle's theorem. So now I have to like look at this and make sure I'm not doing something super duper stupid. I'm always worried that I'm like making some dumb error. Yeah, now I'm like I didn't like vet this one. So okay, well here we go. Now I'm like, let me graph it to make sure it's actually true. I should have graphed it first. Let's look at the graph together though, because why not, right? It's good to actually look at what you're doing. So let's look at the graph just to be absolutely positive. Come on, let's spell Desmos, right? So Desmos, okay. So I'm graphing y equal to, what have I got here? X plus sine squared of x over 3 plus 8. That's, wow, good job, James. Okay. Plus 8. Did I make a mistake? I did, minus 8. Okay. So yeah, it looks like there is only one solution in between. Okay, cool. So, all right. So here's what we're going to do. Let me stop sharing. So to prove uniqueness, we're going to assume there are 2 solutions. Let's call them A and B. Or 2 zeros if you like. Meaning are both equal to 0. Okay. Well, now we're going to use actually what's called Rolle's theorem, which is just a special case of the mean value theorem. So I'm just going to write it like mean value theorem. So here's what we know. F of x, which is equal to x plus sine squared of x over 3 minus 8. This function is continuous. And it's certainly continuous on the interval from a to b. And it's also differentiable on the open interval from a to b. So this function satisfies the hypotheses of the mean value theorem, meaning that its conclusion has to be true. So then we could say, by the mean value theorem, really Rolle's theorem, but Rolle's theorem is just a special case where f of a and f of b are equal to each other. By the mean value theorem, there is a number c between a and b such that f prime of c equals f of b minus f of a over b minus a. But we know that f of b minus f of a is just 0, because f of b and f of a are the same. So this is where it goes from being the mean value theorem to actually the special case of being Rolle's theorem, because this is just 0 over b minus a. And I want to point out, b and a are not equal to each other, right? A and b are different. There are two different zeros. So 0 divided by not 0 is 0. Okay, so far everything we've said is true. If there are two solutions, well, we know the function is continuous and differentiable, so we know the mean value theorem is true. And so between those two solutions, right, essentially we're saying if there's two solutions, which obviously the graph said that there weren't, if there's two solutions, between those two solutions, somewhere the derivative has to be 0. But now we're going to see that the derivative can't be 0, and that's where we're going to get our impossibility. So we take the derivative of this thing, look what we get. We get that the derivative is equal to 1. Oh, I gotta be careful here. The derivative of sine squared of x over 3. This is really sine of x over 3 quantity squared. So taking the derivative, use the chain rule. It's going to be 2 times my stuff times the derivative of my stuff. And the derivative of my stuff is cosine of x over 3 times 1/3. And the derivative is 0. And what the mean value theorem says is that this should be able to equal 0. There is a solution. Okay, but let's check that out. This is where, and often with these problems, this is where your knowledge of sine and cosine is going to be super duper important. I don't want to erase anything. Fine, I'll erase this. So here's what, and then we'll take a break after this problem, and then we'll come back and talk about graphs. So looking at this, here's what I've got. I've got 1 plus, see, 2 times 1/3 is 2/3. So I've got 1. Okay, let's try that again. I've got my derivative is 1 plus 2/3 times sine of the thing x over 3 times cosine of x over 3. And I'm saying this is equal to 0 somewhere. And now here's what I want to say. This can never equal 0. What's the smallest? Oh, I could be, it could be super tricky about it. I'm not going to be that tricky about it. If you want, I'll be tricky about it in a second. Sine and cosine. Let me ask you guys, if I multiply sine of a thing times cosine of a thing, what is the most negative this could be? Let's think about it this way. Sine has to be between 1 and -1. Cosine has to be between 1 and -1. If you take two things that are between 1 and -1 and multiply them together, the most negative they can be is -1. Are you guys cool with that? Do you want me to say more about it?
It's cool.
All right, it's cool. So then here's the thing. If the most negative this can be is -1, 2/3 times -1 is -2/3. And 1 plus -2/3 is 1/3. So the smallest this whole thing can be is 1/3. And 1/3 is definitely bigger than 0. So the problem is the mean value theorem says that this has to be able to equal 0, but our math sense tells us that this can't be equal to 0. So this is what's called a contradiction. We have contradicted something that we know to be true. And so our original assumption, that there are two solutions, was the only thing that could have been wrong, because everything else we did was logical and correct. So this is not true. So that's how these problems typically work out. If someone asks you to show that something has one and only one solution, or exactly one solution, you first have to show there is one. Maybe you can find one, maybe it's an easy thing, or maybe it's a use the intermediate value theorem to show there is a solution. And then the second part is to show it's unique by assuming that there are two solutions and then showing typically that you can't solve the derivative equal to 0. And you have to be able to have the derivative equal to 0, because if there's two solutions, there's a place where f of a equals f of b equals 0, and then between that place, there has to be a place where the derivative is equal to 0. But the derivative is always positive, so we can't be 0. F of x equal to, here, here's my classic favorite example. X cubed minus 6x squared. So I would like to know where this function is increasing and decreasing, where it has relative maxes and relative mins. And so here's the thing to remember or to know. A function can have a relative maximum or a relative minimum where the derivative is either 0 or the derivative is undefined, as long as the original function is still defined. In other words, f of x can, but doesn't have to, have a relative extrema at a critical point. And that is, a critical point is where the derivative is equal to 0 or is undefined. Okay, so let's find, so we're going to use where the derivative is 0 undefined to then find where the derivative is positive or negative and talk about where the function is increasing, decreasing. And so this should also say a function is increasing where its derivative is positive. So f of x is increasing if and only if f prime of x is positive. And similarly, f of x is decreasing when the derivative is negative. Okay. Yeah. So I'm going to find the critical points. So let's look at, let's use the other side of the board. Why not? So here's our function, x cubed minus 6x squared. And here's the derivative. It's 3x squared minus 12x. I'm going to set this equal to 0 or undefined, but I typically don't write down that it might be undefined if I know it's not undefined. You know, this is a polynomial. Polynomials are always defined everywhere. So now I'm going to try and solve this by factoring. So we have 3x times x minus 4, 0. So I get x equal to 0, and I get x equal to 4. And then I think it's very beneficial to make a number line chart with your critical values on it. This is, in my opinion, the most succinct, fastest way of doing this. So there's my critical values, 4 and 0. And here's my, I'm looking at what my derivative is doing, right? I'm not looking at my original function, I'm looking at my derivative. And I also want to say it's usually going to be your benefit or in your interest to look at the factor form. So that's going to be the easiest way to tell if the derivative is positive or negative. So pick a number larger than 4, like 5 or 5 billion, and plug it in. You don't really plug it in. 3 times 5 is positive, 5 times 4 is positive, a positive times positive is a positive. Great. Now you can either keep plugging in numbers like 2, 3 times 2 is positive, 2 minus 4 is negative, positive times negative is negative. Or you can use the fact that the 4 came from this factor. This factor has an odd multiplicity. And when a factor has an odd multiplicity, the sign changes because you cross the x-axis and you go from being positive to negative. Same deal for 0. 0 came from this factor, which has an odd multiplicity. So when you cross there, or when you hit the point 0, you're going to go from being negative to positive. Or you can pick negative 2, and 3 times negative 2 is negative, negative 2 minus 4 is negative, and negative is positive. And then I think it's a good idea to say, oh, if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. If the derivative is positive, the function is increasing. I like doing that. So here's what I can say about this function. I can say that f of x is increasing on the interval from negative infinity to 0, union 4 to infinity. Most textbooks, including yours, says that intervals of increasing or decreasing are always open intervals, so we don't include the endpoints. There is some weird, I think, 17 series textbook. I think they actually do include the endpoints, which just seems weird to me. This function is decreasing on the interval. I mean, I can make an argument for including it, actually, but whatever. It's decreasing on the interval from 0 to 4. And we can also then use the first derivative test to see where we have a relative max or a relative min. And here's the real gist of it. So you can write out a lot of words to say, okay, if you got a function and it's increasing to the left of a critical value and decreasing to the right, it's relative max. I'm just going to look at this picture. My function was getting bigger and then it was getting smaller. Oh, it must have been as big as possible right there at 0. So we have a relative maximum at x equal to 0 because it was increasing and then it was decreasing. That's what the first derivative test says. If you go from left to right, it has to be from left to right, and you go from increasing to decreasing through a critical point, then it had to be a relative maximum. In a similar way, go from left to right, if you go from decreasing to increasing, you have to have a relative minimum. So we have a relative minimum at x equal to 4. We could also find the y values if we wanted to graph it. I'd have to go back to the original function though. The y value here, f of 0, if I plug in 0, I do get 0. The y value here, if I plug in 4, it's easier to factor this. So I really should write this as x squared times x minus 6. And now if I plug in 4, I get 16 times negative 2, which is negative 32. So I'm not really saying we should be graphing things just yet. I just want to kind of point out what the graph looks like. So here's what I get. I get the point 0, 0. I get the point 4, negative 32. And I will also mention, just because it's an important point, x equal to 6 is also an x-intercept. So here's what I get. And so I really like this sign chart for graphing because like the first derivative sign chart really tells me what the function looks like. The function is increasing until I get to 0. It's decreasing until I get to the point 4, negative 32. And it's increasing after that. So it's going to look like this. So, there. Okay, yeah, perfect. Increasing, relative max, decreasing, relative min, increasing. Okay, let's do some more. Again, please stop me or interject if you have questions. Let's see. Yeah, let's do that.
Can we do a function with e, maybe?
Yes, definitely. I want to do something else first, but yes, we can definitely go in with e.
Cool.
But yeah, I want to talk about. Yeah, let's do that one. Let's do this. Let's do g of x equal to. I want to do that one, really. Let's do this one. Let's do g of x equal to x squared over x minus. Let's do x minus 3. No, I'm sorry. I'm going to change that. I know I want to do this. Yeah, okay. Let's do x cubed over. That's lame too. Sorry, I'm like, okay, fine. I've got it. I know what I want. It's just. Sorry, come on, brain. Yeah, I guess that'll be fine. I'm going back to my original. Let's go x squared over x minus 3. Sure. This is probably terrible. It's fine. So let's find the, and again, same questions. We want to know where it's increasing, decreasing, what the critical points are, or what if there's any relative extrema. So let's find the first derivative. The bottom times the derivative of the top minus the top times the derivative of the bottom is just 1 over the bottom squared. So g prime of x, simplifying. You do, this is, so these ones where you're graphing things and you're trying to find critical values, this is where you definitely do have to be able to simplify the derivative. So I'm going to get, let's see, multiply this out, I get 2x squared minus 6x minus x squared. I don't need to multiply at the bottom. So I get g prime of x equals 2x squared minus x squared is just x squared minus 6x, x minus 3 squared. And then I think it pays to factor. So I'm going to factor out an x from the top. I've got x times x minus 6 over x minus 3 squared. What are my critical points? What are the values of x that make the derivative 0 or undefined? Or critical values, I should say. Well, let's see. What makes it 0? 0 for sure. What else? Give a guy a mirror and see what happens. Yeah. Those are the two values of x that make the derivative equal to 0. Okay, I'm going to ask kind of a loaded question here. What value of x makes this derivative undefined? Right. Okay, so here's what I want to say. X equal to 3 maybe gets an asterisk. It's what I call a pseudo-critical value. Here's what I will say. We should just include it. As far as I'm concerned, we need to, especially if we want to know where this thing is increasing or decreasing, that is definitely an important place. Here's why I'm hesitant or calling it a pseudo one, because x equal to 3 is not in the domain of the original function. We know in this function we have a vertical asymptote at x equal to 3. So we know we couldn't possibly have a relative max or a relative minimum there. But the function can change from increasing to decreasing there. So it really is important to include these values where the derivative is undefined, even if they're not in the domain of the original function. I'm going to say that one more time. It's really important to include these values where the derivative is undefined, even if they're not in the domain of the original function. They won't be where we have relative extrema, but they will be where we might have the function change from increasing to decreasing or decreasing to increasing. Okay, so let's take a look. So here's my number line with all of my critical values at pseudo or otherwise, 0, 3, and 6. And here's what I'm going to point out. X, where the 0 came from, and 6, where the x minus 6, or sorry, and x minus 6, where the 6 came from, both have odd multiplicities. And x minus 3, where the 3 came from, has an even multiplicity. So let's start over here. We pick a number larger than 6, like 9. 9 times 9 minus 6 is positive over 9 minus 3 squared. It's still positive. So the whole thing is positive, which means I know the function is increasing. Okay. From here to here, is the sign changing or staying the same? Well, 6 came from this, which has an odd power, so the sign's going to change. Or you can pick a point. Pick 4, plug it in, positive, negative, positive, so the whole thing's now negative. 3 came from this factor, which has an even multiplicity, so the sign's going to stay the same, so it's still negative. Or you can pick a point. Pick 1, positive, negative. Negative squared is still positive, so positive times a negative times a negative. Sorry, positive times a negative times a positive is still negative. Finally, over here on the other side of 0, 0 came from this factor, which has an odd multiplicity, so it's going to change signs. Or pick negative 1, negative, negative, positive means the whole thing is positive. Okay, so I'm going to say the function is increasing, then decreasing, then decreasing, then increasing. So here's what we have. So let me ask you guys, where do we have a relative maximum? At 0, at 3, or at 6? Anybody? So we have a relative maximum where it goes from left to right, increasing and then decreasing. The relative maximum at 0. We have a relative minimum when it's the reverse of that, when it's decreasing and then increasing. So relative minimum when x is equal to 6, because it goes from decreasing to increasing. We don't have anything at 3 because we have a vertical asymptote at 3. Okay, if we were to talk about the intervals where this thing is increasing. So this thing is increasing on the interval from negative infinity to 0, union 0 to infinity. Union what? Not 0 to infinity. Don't be crazy. Union 6 to infinity. Sorry about that. This thing is decreasing. But this is where things get a little tricky. Decreasing from 0 to where? Well, here's the thing. You can't be decreasing at the point 3 because the function isn't defined at the point 3. So it's decreasing from 0 to 3 and from 3 to 6. Graphically, here's what's going on. So here's what this function looks like. Real quick, you've got a relative maximum at 0, 0. I just erased my function. That was brilliant. My function was x squared over x minus 3. When you plug in 0, you get 0. It's got a relative maximum there, meaning it is increasing beforehand and decreasing afterwards. Here's my vertical asymptote at x equals 3. And then after 3, the function is decreasing until you get to 6, and then increasing afterwards. And if you plug in 6, you get 36 over 3, which is 12. So 612 is a relative minimum, right? It's smaller than all the stuff right next to it. 0, 0 is a relative maximum. It's bigger than all the stuff that's right next to it. Neither one of them are absolute. 0, 0 is not an absolute maximum. There's lots of values that are bigger than it. In fact, this minimum is bigger than the absolute, or than this maximum, right? And there is no absolute minimum, right? There's no smallest value because it goes up to infinity, not negative infinity. There was something else. Yeah, so, but it would be very, very wrong to say that it was decreasing on the interval from 0 to 6. Let's see what time is it. Yeah, okay. one more very brief example before I do an e to the x example. Definitely do an e to the x example. If you have one in mind, Riley, I'm perfectly happy. I think it was Riley who said that anyway. I'm not positive. I see Riley's face all the time because he has a picture up, so I'm like, maybe it was Riley. Whoever said e to the x, if you have a specific example, feel free to type it in the chat. Otherwise, I'll just come up with something. But I want to look at one more example very, very quickly. Where is this function? X cubed, increasing / decreasing. I want to point out the difference here. So, yeah, let's just do it and then we'll talk about the difference. So find the derivative, super straightforward. F prime of x is 3x squared. Find the critical value, so I'm going to set the derivative equal to 0. Solving this, x is 0. So here's my number line. 0 is my only critical value. If I pick a number larger than 0, like 1, plug it into the derivative. The derivative, f prime of 1 is positive. So the function is increasing. Pick a number like like -1. F prime of -1, still positive, right? -1 squared, 1 times 3 is 3. So this function is increasing and then increasing. So here's what I would say. This function is increasing on the interval from -infinity to infinity. And the difference is that this one is decreasing, but it's undefined between the decreasing places. So we can't include where it's undefined. This function is increasing, but it is defined at the place where it's in between the two increasing intervals. So we do include that value. Right, here's what the function looks like. I know you guys know what x cubed looks like. It looks like that. To be increasing on an interval, so the idea of the way we define a function as increasing, or the definition of being increasing, is if, say, b is bigger than a, then f of b is bigger than f of a, which is totally true. And in this function, it is totally true even if 0 is one of the 2 points you pick, right? If 0 is less than a number, then f of 0 is certainly less than f of that number. And if 0 is bigger than the number, then f of 0 is certainly bigger than f of the number. So this function is increasing on the entire interval. Even though it flattens out for 1 point, it still is increasing on the entire interval. I will also say this function has no relative extrema. Right? There is no place where it goes increasing, decreasing, or decreasing, increasing. Okay. Are there questions about this one before we go on? Okay. So the question that Will just wrote offers a good contrast to the relative extrema questions we've been asking. So let's do this one that Will asked, and then we'll do another one here. Yeah. So let's see, we've got f of x equal to 1 over x plus the natural log of x on the interval from e to the -1st to e to the 2nd. Let me just see 1 sec here. Try to do, sorry, 1 sec. So, how do you find the absolute maximum and minimum of this? Good question. So, I'll remind everybody the difference between an absolute max and a relative max, or I should say, the difference between absolute extrema and relative extrema, is that for relative extrema, we're doing what we just did before, where we find where it's increasing, decreasing, or decreasing, increasing. Absolute extrema is actually very different. We're still going to find the critical values, and that's kind of the only part that's the same. So let's find the critical values. So I got to find the derivative of this. So the derivative of this is, let's see. Derivative of x to the 1 over x is, I'm going to write this as x to the negative first plus the natural log of x. So the derivative of this is negative x to the negative second plus 1 over x. And I want to find the critical values. Oof, I need to simplify this. So if I were simplifying this, I would probably want to rewrite it in the following way. I write it as negative 1 over x squared plus 1 over x. I might even change the order to write this as 1 over x minus 1 over x squared. What should I do now?
Check the
endpoints. You were right that I want to check the endpoints, but before I check the endpoints, I really want to find the critical values. So to find the critical values, I'm taking this and setting it equal to what?
0. Yeah.
Or undefined. What makes this undefined? For sure.
0.
Same answer, right? 0, yeah. So 0 makes this undefined. What makes this equal to 0? This one you might be able to see it without actually doing the simplifying.
1.
1 does, right? And this one you kind of luck out in that you can see that 1 makes this 0, right? 1 over 1 minus 1 over 1 is 0. However, sometimes things aren't always as easy. And so the process we should really use here is getting a common denominator. So I multiply this by x over x. I'm going to get x over x squared minus 1 over x squared. And then it's easier to see, maybe not easier, but it's more of a consistent process to see that, oh yeah, you're going to get x minus 1 equal to 0, which is going to give us x equal to 1. And then also x equal to 0. Okay, so now this is where things diverge completely from what we were doing before. To see if this is an absolute max or an absolute min, or I should say, to see what the absolute max is and what the absolute min is, we have to check these values in our original function. So we're going to look at f of 1 and f of 0. And yes, we are also going to check the endpoints like we were told to. F of e to the minus 1, f of e to the minus 2. So what's f of 1? Well, I'm going to plug it back into the original function. So I'm going to get 1 over 1 plus the natural log of 1. What's the natural log of 1? 0. This is just 1. What about f of 0? That seems problematic. Is 0 problematic? Well, yeah, I mean, it is, right? Plug in 0, you're definitely going to be undefined. Oh, I thought there was something about the extreme value theorem that said you can only use the extreme value theorem if the function is defined and continuous on a closed interval. It's not defined at 0. What are we missing here? What are we missing here? Anybody have a suggestion? Thought?
Oh, 0 is not in the domain.
0 is not in the interval, right? Because this is really 1 over e to e squared. So we shouldn't be considering 0 at all. Even though it was a critical value of the original function, I mean, not really, because it's not in the domain, but like, still, 0 is out of bounds. Now let's do f of e to the negative 1. So I'm going to get 1 over e to the negative 1 plus the natural log of e to the negative 1. That's not as bad as it looks. 1 over e to the negative 1 is just e. And the natural log of e to a thing is just the thing. So the natural log of e to the negative 1 is just negative 1. See, e minus 1. And then I wrote negative 2 here, but that should be a positive 2. Same idea here. F of e squared is going to be 1 over e squared plus the natural log of e squared, which is going to be 1 over e squared plus 2. All right, so here are my numbers. My numbers are 1, e minus 1, and 1 over e squared plus 2. Which of those is the smallest? 1, e minus 1, or 1 over e squared plus 2? Well, we know e is about 2.7. This is about 2.7 minus 1, so about 1.7. And this is 2 plus a pot, that's way bigger than 2. Not way bigger, it's bigger than 2. So 1 is definitely the smallest. And likewise, we can see that of these two, well, this one's bigger. This is 2 plus something, and this is about 2.7 minus 1, which is less than 2. So I would say if I was asking what the maximum value is, the maximum value is that number, 1 over e squared plus 2. It occurs at e squared. The minimum value is 1, and it occurs at 1. So this is very different in my opinion. I mean, it's different but the same. It's the same because we're finding critical values, but it's different in that we're not using the first derivative test to see if we have a relative max or a relative min. We're plugging the functions back into the values back into the original function to see if it's a maximum or an absolute maximum or absolute minimum. Okay, so yeah, I definitely have another one I want to look at. I think I have 2 more good. Well, I have lots of good examples, but I have 2 more specific examples I definitely want to get to. Let me just see, where'd you go? Yeah, fine. Okay, so let's look at the following function, even though I'm not thrilled about it. Let's look at f of x equal to x over x minus 1 squared. And I want to find the relative extreme of this function, and also where it's increasing and decreasing. All right, so first and foremost, let's find the derivative. I don't think we're going to get to inflection points today, but we can definitely talk about inflection points on Wednesday. So, okay, we have to be a little bit extra careful here. Yeah, well, so I'm going to, okay. The rule, the quotient rule. Bottom, derivative of the top, minus the top. Derivative of the bottom, the derivative of x minus 1 squared is 2 times my stuff to the first times the derivative of my stuff, or just 2 times x minus 1, over x minus 1 squared squared. Now, here's the thing about using the quotient rule. If your denominator is already to a power that's higher than 1, you should always be able to factor out some amount of that. Really, here's what actually happens. When you do the quotient rule, your denominator's power should increase by 1. I know we square the denominator, but if you simplify and factor, you always end up getting the denominator just having a 1 higher power than it had before. So what I'm saying here is that after I simplify, I should be able to have an x minus 1 cubed in the denominator. I should be able to cancel one of those x minus 1s. And it works. I can factor out an x minus 1 from each of these pieces here. So I get x minus 1 times, so here I'm left with an x minus 1, minus here I'm left with a 2x. To the 4th. And then I can cancel one of them. Cancel this one and cancel this one. Simplifying the numerator, x minus 2x is negative x. So I get negative x minus 1 over x minus 1 cubed. All right, I want you guys to help me out. Clearly, this is undefined when x equals 1. So even though it's not a true critical value, because it's not in the domain, I'm still going to call it a critical value. What's my other critical value? What makes the numerator equal to 0? Thank you. Yeah, negative 1. And the way you can solve that is just by set negative x minus 1 equal to 0. You can even just factor out a negative 1 if you want. Negative 1 times x plus 1. Oh, yeah, of course x has to equal negative 1. So x is negative 1. So those are my critical values. Let's look at the sign chart. Also, I will actually point out, I do really think it's worthwhile to actually factor out the negative 1 and write this as negative x plus 1 over x minus 1 cubed. Be careful. I've definitely seen people factor this out wrong and say it's negative x minus 1 and then try and cancel another x minus 1. Nothing cancels here at this point. You're stuck with this. So my critical values are 1 and negative 1. I don't put 0 on there unless it's a critical value. And then I'm going to look at what this is why I want my derivative factored so I can see where it's positive, where it's negative. So pick a number larger than 1, like 2, plug it in. The top is negative 3. The bottom is positive 1. The whole thing is negative. Pick something between negative 1 and 1, like 0. Or use the fact that 1 came, from this factor, just an odd power, which means the sign's going to change. Or pick 0 and see that the top is negative, the bottom is also negative, and the negative over negative is a positive. Finally, pick something less than negative 2, less than negative 1, like negative 2. The top is going to be negative negative 1, so positive. The bottom is going to be negative 3 cubed, so negative, and a positive over negative is negative. Or negative 1 came from this factor, which is also to an odd power of 1. And when it's to an odd power, the sign changes. So this function is decreasing, increasing, decreasing. Okay, let's write down the stuff. So f of x is increasing on the interval from negative 1 to 1. It's decreasing on negative infinity to negative 1. Union 1 to infinity. And I'm going to erase some of this so I can write some stuff. So let me ask, do I have a relative minimum? Yes? No?
Yeah, negative 1.
Right. Relative minimum, yes. At x equal to negative 1. Do I have a relative maximum?
Yep. X equals 1.
No.
No.
So, but I really was hoping you guys would say yes. So don't feel bad that you got tricked. I definitely led you down the path of getting tricked on purpose. I don't have a relative maximum there, even though it's increasing to decreasing. Why not? I've got a vertical asymptote at x equals 1. It cannot have a maximum at x equals 1 because it's not defined there. Here's what this function looks like. But please don't feel bad about falling for my trap. I definitely set a good trap, and you guys, as I wanted you to, walk right into it. But I appreciate it because I was hoping someone would say that. But here's what we've got. We've got our function. So at positive 1, we have a vertical asymptote. And so if I plug in negative 1, I get negative 1 over negative 2 squared, which is negative 1 over 4. So I plug in negative 1, I get negative 1/4. And then when I plug in 0, I get 0 just to have the intercept there. So here's what's happening. This function is decreasing from negative infinity to negative 1. It's increasing from -1 to 1. And it's decreasing afterwards. So I definitely have a relative minimum right there at -1, -1/4. It's also an absolute minimum because it's the smallest thing on the graph for sure. But I don't have a relative maximum. Even though it's increasing and then decreasing, to have a relative maximum, you have to have those two things, and part 3, it has to be defined there. So it has to be increasing, decreasing, and defined. So that's why, I'm going to go back a little bit. That's why I call x equal to 1 in this case. I call this a pseudo-critical value because it's important to include. Right? It's definitely important to know to answer the question about increasing, decreasing if the derivative changes from positive to negative when you look at that part. But technically, it's not a critical value. And the important part about that is that if it is increasing, decreasing, or decreasing, increasing, we can't say it's a relative extrema. So when you are looking at functions like this and trying to graph them and classify all your relative extrema, I would really encourage everyone to start off by saying, x can't be 1. I have a vertical asymptote there. I cannot possibly have a max or a min. Not possible. I would always encourage you before. And so I think next class we'll talk about kind of more the process for graphing things. But the process for graphing things that I usually take myself through is first find the y-intercept, then find the x-intercepts, then find the vertical asymptotes, then find the horizontal asymptotes, then find the first derivative stuff, meaning increasing, decreasing, relative extrema. And then find the second derivative stuff, meaning, which we haven't talked about yet, concave up, concave down, and any even function points. So if you follow that process, before you even get to talking about relative maxes and relative mins, you'll be like, oh, I have a vertical asymptote somewhere. Nothing else can happen at a vertical asymptote. It's off limits. Yeah. I feel like there's something else I want to say here. Maybe not. Let me throw one more quick example at you guys because we have a minute. Let's say I wanted to find the relative extrema for the following function. Let's say my function is x cubed times e to the x. I want to find the relative extrema. So take the derivative, product rule, 3x squared times e to the x plus x cubed times the derivative e to the x to e to the x. Find the critical values. Observe that this function is never undefined. Right? Just like when we talk about domains of functions, we're looking for 3 kinds of things that make things undefined. Square roots of negatives, logarithms of zeros or negatives, or division by 0. We have none of those issues here. There's no division, there's no square roots, there's no logarithms. So we don't have any places where this could be undefined. So I can factor in x squared e to the x. I'm left with a 3 plus an x. And I see I have 2 critical values. X equal to 0. E to the x equal to 0. That never happens. E to the x is always positive. And 3 plus x equal to 0. So x equals to -3. So those are my critical values. Throw them on the number line. And look at where your derivative, right? It's always what your derivative is doing. So pick a number larger than 0, like 1. 1 squared is positive. E to the whatever is always positive. And 3 plus 1 is positive. Pick a number less than 0, like -1. -1 squared is positive. E to the -1 is positive. 3 plus -1 is positive. Or you could have said 0 came from this factor with an even multiplicity, meaning the sign stays the same. And then finally, -3 came from this with an odd multiplicity, so the sign's going to change. Or you could say pick -4. -4 squared is positive. E to the -4 is still positive. It's always positive. And 3 plus -4 is negative. Positive times positive, negative is negative. So our function is decreasing, increasing, increasing. Meaning, well, we could, actually, that's a good thing to talk about here. So we could say it's decreasing on the interval from negative infinity to negative 3. It's increasing on, all right, let me ask you guys, I know we're out of time, but let me ask this real quick question. Do I have to break it up at 0 or not? Yes, break it up. No, don't break it up. No, don't break it up, right? It's defined at 0, so it's not only okay to, we have to include 0 and say it's increasing from negative 3 to infinity. And finally, we have a relative minimum at negative 3. I will also point out, because I think it's kind of cool, with this information, you can do a pretty good job of graphing the thing right off the bat. I'm going to erase this real quick. Here's what I know. I know from negative infinity to negative 3, it's going to be decreasing. So when I plug in negative 3, I get negative 27 times e to the negative third, which is like negative 27 over e to the third, which is not much smaller than negative 1. E cubed is something. Anyway, it's slightly negative. So I know it's decreasing from here to there, increasing after. I have 0 as a point. Right? It hits the intercept of 0, and then it keeps getting bigger. And maybe it does something kind of funky here. I don't know. But like, just from the first derivative chart, you can get a pretty decent idea of what the function might look like.